NASA has achieved a breakthrough in rocket propulsion with a revolutionary test of a rotating detonation engine. This 3D printed rocket engine could increase fuel efficiency by up to 5%, a significant gain considering rocket weights are largely determined by fuel. The test was made possible by the latest advances in materials, science, and computational fluid dynamics, marking a major step forward in space exploration technology. The first stage, Saturn V, had a hydraulic mass of 137,000 kilograms when fully loaded with propellant. Its weight was 2.2 million kilograms. The first stage was 94% fuel. A 5% increase in fuel efficiency represents a 103 tons decrease in fuel. That's not far off the total dry mass of a Falcon 9 rocket. Rocket technology has taken a huge leap forward with the development of rotating detonation engines, which can launch larger payloads further into space while using less fuel. The recent successful test of this groundbreaking technology involved the engine firing 18 times with a maximum duration of 113 seconds per run. Although not yet ready for use, this achievement is the result of decades of research and cutting-edge manufacturing techniques. So, how do these engines work? By using a ring-shaped combustion chamber, a supersonic flame front is created, resulting in consistent thrust and solving the problems of unreliable and pulsating thrust associated with pulse detonation engines. Harnessing this phenomenon is incredibly difficult, but the benefits of rotating detonation engines are clear. These were, in fact, detonations that were destroying the engine. On June 28, 1962, these combustion instabilities caused an engine to be completely destroyed during testing. This problem was plaguing the engineers of the Saturn V, and it is arguably the greatest challenge they faced in scaling this monstrous rocket to reach the moon. A list of 18 potential sources for the instability was made. This was an incredibly complex and dynamic problem. One method to reduce instabilities and to prevent pressure waves from amplifying off the sidewalls like a sound wave was to install baffles that separated the combustion chamber radially. Several iterations of baffles were designed, but with no computational method available, the engineers of the FON engine turned to the next best practical method. They set off tiny bombs inside the combustion chamber during operation to quickly induce small combustion instabilities. Engineers have been trying to prevent uncontrollable detonations for decades, but the quick release of energy from detonations is what makes them dangerous yet appealing. A new metallic 3D printing material, developed by NASA, could help harness this energy. The alloy has a high melting point and thermal conductivity, making it ideal for handling the rapid changes in temperature and pressure that occur during a detonation cycle. To handle backflow, engineers can turn to fluid diodes, which can be easily manufactured with 3D printing. The possibilities of using metal 3D printing in engine manufacturing are endless. Every part of the rotating detonation engine requires delicate shaping to harness the power of detonation. From the combustion chamber designed to ensure the shock wave remains in rotation to the tiny cooling channels running through the walls. The rotating detonation engine that NASA developed used a 3D printed thrust chamber that was actively cooled using deep ionized water. It also features an aerospike nozzle. Aerospike nozzles are kind of like inside-out nozzles instead of the traditional bell-shaped nozzle. It features a cone at the center of the exhaust. Energy loss is a common problem faced by engines when operating in the underexpanded condition. This occurs when external pressure is lower than the exhaust, resulting in the gas expanding outwards and wasting valuable energy. But fear not. There is a solution to this problem that can make your engine more efficient. By matching the exit pressure and atmospheric pressure, you can maximize your exhaust velocity and minimize energy loss. Sure, you could fit rockets with variable geometry nozzles like fighter jets, but that would add unnecessary waste, complexity, and cost. That's where the game-changing aerospike nozzle comes in. Unlike the bulky and expensive variable geometry exhausts, the sleek aerospike nozzle provides a lighter, simpler alternative. As external atmospheric pressure changes, the aerospike automatically compensates and redirects the exhaust to point straight down, ensuring no flow separation occurs. Plus, its circular combustion chamber design is perfectly suited to the needs of rotating detonation engines. We could go on and on about the intricate science behind these amazing nozzles, but the bottom line is that they are a game changer. And optimizing the design of your Bell nozzle is crucial to ensure consistent chamber pressure and achieve the best possible expansion ratio with your rotating detonation engine. So, if you want to take your engineering game to the next level, the aerospike nozzle is the way to go. The chamber pressure is constantly changing along the circumference of the combustion chamber. The aerospike ability to adapt to external atmospheric pressure is also help it adapt to internal chamber pressure changes. There is a lot more to do to make rotating detonation engines viable. These prototypes, while promising, struggled to run for long enough to produce prolonged thrust. In 2021, Japan tested a rotating detonation engine in space, which operated for 6 seconds, producing 500 newtons of thrust. And while this was a proof of concept, it's a long way from the millions of newtons traditional rocket engines can achieve. The mechanics of detonations are still not fully understood. This means that maintaining a stable detonation front is extremely difficult. The system is inherently chaotic. Engineers are fighting against entropy to control these powerful turbulent flow regimes. With each revolution of the shock wave, more chaos is introduced to the system. A single vortex on revolution, one can cause a ripple effect until the rotation becomes completely unstable. By rotation 20, NASA even shared that their tests sometimes fluctuate from having 2 to 5 car rotating detonation waves in the combustion chamber at once. Conclusions. NASA's successful test of a rotating detonation engine marks a significant breakthrough in rocket propulsion. This cutting-edge technology could revolutionize space exploration by increasing fuel efficiency by up to 5%. The engine was developed using the latest advances in materials, science, and computational fluid dynamics, demonstrating the incredible potential of 3D printing and manufacturing. With the help of fluid diodes and aerospike nozzles, this technology could allow rockets to launch larger payloads while using less fuel, opening up a whole new frontier for space exploration.